Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions on AC, quantum physics, astronomy, and nuclear physics from October-November 2022, paper 4, variant 1. In the last video, we have discussed from question number 1 to question number 6 in the last two videos. And for the solution of those questions, you can go to the channel and you can search for October-November 2022, paper 4-1, part 01 and part 02. And in today's lesson, we will start from question number 7 and we will discuss questions from question 7 to question 10. And we will discuss these questions in detail as always we do, so you can improve your conceptual understanding of these topics and also you can have better understanding of these questions. Let's study together, let's improve together. For question number 7, part A, it is given to us a sinusoidal alternating voltage as a root mean square, potential difference of 4.2 volts and a frequency of 50 kilohertz. For part A1, it is given to us the alternating voltage is applied across a resistor of resistance 760 ohms. By considering the peak voltage, we need to show that the maximum power dissipated by resistor is equal to this one. So we need to calculate P. Question is asking you to calculate value of P. So P in DC circuit simply is equal to V squared divided by R. So simply you can write down the formula. Now question is asking you to calculate the maximum value of power dissipated. So this value has to be peak value. So this is how you can come from DC to AC. But in the question we have RMS. So this is VRMS. So we need to convert VRMS into peak value. So simply we can write down peak value. This one will be equal to root of 2 times VRMS. Root of 2 times VRMS. Simply most of the time student they just remember VRMS. So you can also write down VRMS is equal to V peak divided by root of 2. So from here you can go back to V peak. So we need to calculate value of V peak and we have value of VRMS. VRMS is equal to 4.2. Now if you multiply this one, you will get the answer that is equal to 5.9 volts. Now simply you need to plug in these values. And so the V peak is equal to 5.9 squared. Divided by, we have value of resistance that is equal to 760 ohms. Now, if we solve this one, our final answer will be equal to 0.046 watts. And we can convert this one into milliwatts. So simply we have this is 4.6 times 10 to minus 2 and we multiply this one with 1000. So our final answer will be equal to 46 milliwatts. So this is what we need to show. So this is our final answer. And so if you have done this one, in this case you will get 2 marks. For the second part on figure 7.1, we need to draw a smooth curve to show how the power dissipated in the resistor varies with time t. Between t is equal to 0 and t is equal to 40 microseconds. And also we need to assume that P is equal to 0 when T is equal to 0. For this question, frequency is given to us. We have value of frequency of alternating voltage. Frequency is equal to 50 kilohertz. So this is the frequency. So the time period we can calculate from here. Time period will be equal to 1 over frequency. So we have here 1 divided by 50 times we have 10 to 30. And if we solve this one, in this case we will get 2 times 10 to minus 5 seconds. But the given unit is microseconds. So we have to convert this one into microseconds. So we have to multiply this one by 10 to 6. Now if we solve this one, we will get 20 microseconds. So this is the time period. Mean the time period of alternating voltage is 20 microseconds and the time for power, this will be half of that. So it means this is the time period for alternating voltage and the time period for P power repetition, that will be half of that. So that will be 10. So here this is 10. So here it is 10. So it means 4 half cycles you have to draw. So in this case, total power was given to us, power dissipated in the resistor. P max was given to us. We have just calculated that is equal to 46 46 milliwatts. 46 milliwatts. Now, if you look at the given scale, we have 0 to 25 and we have 10 small square. So one small square, we can say in this case, one small square is equal to 2.5 milliwatts. So this one is 50. So this will be 47.5 and this will be 45. So the 46 will be a little higher than 45. And also we need to understand the peak will be at the half. So you have 1, 2, 3, 4, 5. So the one peak will be here at this point. And we can also count 5 here. 1, 2, 3, 4, 5. So the peak will be here. We can also count here 5. 1, 2, 3, 4, 5. So the peak will be little above 45. And here 1, 2, 3, 4, 5. So peak will be here. Now simply we need to draw 4, in this case, half cycles. So this is how you can draw. Look at this one. This is in a nicer way you can draw. So this is how you can draw, and the shape should look like this one. So you can see we have drawn these 4 cycles. Actually, for alternating voltage, this is one complete cycle, and this is the time period we have calculated, and the power is the half. So it is repeating because power is I square. So that's the reason this negative side, this flip. So we have 4 here. So if you draw like this, you will get 3 marks for this question. And this is a typical type of question. So you have to be clear about this one. How to sketch power against time. For third part, we need to use our graph from A2, and we need to explain why the mean power dissipated in the resistor is 23 milliwatts. Maximum power dissipated in the resistor we have just calculated, that was equal to 46 milliwatt. Now we need to explain why the mean power is equal to 23 milliwatts using this graph, means using this sketch. If you look at this sketch, this is not accurate sketch. This is just a rough sketch, and this one is accurate one. So I will explain you with the help of this. So in this case, we have the graph I square against time. So the power in this case will be equal to I naught squared times R. So this one is the maximum power, and power, mean power for here, this one will be equal to I naught squared times R divided by 2. So this is the mean power. Mean power means that is certain value of the power that is always across the resistor, because the power is changing. You can see that power is changing between 0 and 46. So question is asking you what is the average value for this one. So the average value we can calculate. So if we divide this one into 2 parts from here, if you cut this one and you take this part and you place this one here, so you see this is part. So we can place this part here, and if we cut this part here, this will be at this point. So you can see now the power is just a horizontal line, and this is 23 milliwatts. And the same you can do for this one. You can cut this one here and you can fit here, and this part you can fit here. So in this case, the average power dissipated in the resistor is equal to 23 milliwatts. Question is asking us to explain with the help of the graph. So simply we can say in this case the line is symmetrical about 23 milliwatts. Mean this is the power that is always dissipated in the resistor. So this will be here, and if you cut this one, for example, this part you can fit here, and this part you can fit here, and so on. So this part you fit here, this part here. So the power dissipated, average power dissipated across the resistor is equal to 23 milliwatts. So if you look at this sketch, in this case 23 will be, this is 25, and this one will be 22.5. So 23 will be around here, about here. So it will be, it is symmetrical about this part, symmetrical. So simply you can say in this case line is symmetrical about 23 milliwatts. If you write on this point, you will get 1 mark, and that is the B mark. So this mark will be B mark. For part B, it is given to us the alternating voltage in A is now applied to a piezoelectric crystal in air. For part B1, we need to explain what happens to the air surrounding the crystal. But one thing we need to understand is that frequency of alternating voltage is 50 kilohertz. This frequency was given to us in part A, and this frequency is in ultrasound range. So first of all, we can write down this is in ultrasound range. This frequency is in ultrasound range. Now we need to understand if we apply alternating voltage with this frequency, across the piezoelectric crystal. So this is our piezoelectric crystal. This one is the crystal. And now if we apply alternating voltage across this one, what will happen to this crystal? When we apply alternating voltage across this crystal will vibrate like this. So it will be compressed and it will expand, compressed, expand, compressed, expand. So it will be compressed and it will expand like this. So the surrounding air also will be compressed with the same frequency, and it also will expand with the same frequency. So the air surrounding also will be compressed and also it will expand at the same frequency as frequency of alternating voltage, because crystal is vibrating at the same frequency. So in this case, we will say first thing, alternating voltage will cause the crystal to vibrate. So the crystal will vibrate, and when this crystal will vibrate, crystal will cause air to vibrate, means the surrounding air vibrate. Surrounding air will vibrate, and surrounding air will vibrate at a frequency in ultrasound range. So these 3 points you need to understand. If you write down these 3 points, you will get 3 B marks. So that's all. First of all, when you apply alternating voltage, crystal will vibrate. And when object is vibrating objects produce sound waves. And the frequency of sound waves and frequency of vibration of the crystal will be the same as frequency of alternating voltage. So these points you need to understand. So if you have understanding of this one, so in this case, we can write down our answer like this. So these 3 points you can mention in your answer. You can say alternating PD makes the crystal to vibrate, and the vibrations of the crystal cause air to vibrate, and air is vibrating with this frequency. That is the frequency of alternating voltage. And so these 3 points you have to mention. So in this case, actually, we are producing ultrasound waves. So this one is acting like a transmitter. So very important thing you need to understand. In this case, crystal is acting like a transmitter, means producing ultrasound waves. But this crystal can also act like detector. So that one we will see in the next part. For the second part, it is given to us a second piezoelectric crystal is placed in the air near to the first crystal. Explain the effect of the surrounding air in B1 on the second crystal. In the first case, we have seen crystal is vibrating. So you can look at this one. This crystal is vibrating. So this is our first crystal, vibrating crystal. So this is the first one. So this is first crystal, and this one you can imagine this one is second crystal. So this one is second crystal. Now in this case, first crystal is vibrating due to the applied voltage. So as first crystal is vibrating due to applied voltage, there will be sound waves. So this is producing sound waves. Then when these sound waves, they will hit this piezoelectric crystal. This piezoelectric crystal will be compressed, and this piezoelectric crystal will expand. Because when compression is coming, this will be compressed, and when rarefaction is coming, this will expand. So this crystal will be compressed and this will expand. So in this case, one side of this crystal will be more positive, one side will be more negative, and this process will repeat. Means first time this become more positive, this will be more negative, and then when rarefaction comes, this will be more negative, just imagine, and this will be more positive, and so on. So in this case, there will be alternating voltage across this second crystal. So if we connect our voltmeter here, we will see alternating voltage on this voltmeter. So simply this vibrating air will cause, or we can simply say will induce EMF across this piezoelectric crystal, across the second. Now in this case, this one is acting like a detector. So this second crystal is acting like a detector, and the first one is acting like a transmitter. And this is very important for ultrasound. So you have to be very clear about this one. So the first crystal is acting like a transmitter, and second crystal is acting like a detector. That's reason in ultrasound probe, we only use one piezoelectric crystal that acts like a transmitter. Then same crystal also acts like detector. And for this question, just 1 mark. So if you write down this point, you will get 1 mark. And that is B mark. Air makes crystal to vibrate, which causes an EMF to be generated across the second crystal, and you will get 1 B mark. And this question was conceptual question, not difficult one, but little bit tricky one, because most of the time students, they just try to memorize how ultrasound waves are produced, but they don't understand the whole process. They don't understand the reasoning behind that, or we can say the concept behind that, how ultrasound waves are produced and what is happening to the air surrounding the crystal. So this was conceptual question, and many students, they got confused with this one. They were not clear what to write for this answer. For our question number A, part A, we need to state what is meant by the work function energy of a matter. Work function energy of a matter, simply we can understand with the help of simple diagram. Imagine that we have, this is a piece of metal. So this is piece of metal. It has many electrons. Some electrons, they are at the surface. They are close to the surface. So these are electrons close to the surface. And now if electromagnetic radiation is coming, let's say energy of this electromagnetic radiation, we can also imagine this is a photon. Imagine that this is a photon of EM radiation is coming, and frequency of this one is F. Now we can write down photoelectric effect equation. According to photoelectric effect equation, energy of the photon, this is equal to kinetic energy maximum plus work function. Now in this case, if kinetic energy maximum is equal to 0, then we can say energy of the photon is equal to the work function, and that amount of energy we need, the minimum amount of energy we need to release electron from the surface of the metal with 0 kinetic energy, that minimum energy we call is work function. So we can also say HF naught. So this frequency we also call is threshold frequency. So F naught in this case is representing threshold frequency. So this is threshold frequency. So next time they can ask you about what is threshold frequency. So this is threshold frequency, means the minimum frequency required, minimum frequency of electromagnetic radiation required to release electron from the surface of the metal with 0 kinetic energy. So you can also define threshold frequency. So in this case, when this electron will be released from this metal, it will sit here, but its kinetic energy will be equal to 0. So that energy of electromagnetic radiation is equal to work function of the metal. If energy is greater than work function of the metal, then electron will have some kinetic energy. So this is how you can write on your answer. So in the answer, you have to mention minimum is very important. Minimum photon energy required to remove electron from metal surface with 0 kinetic energy. This question has 2 marks. So if you have written first part, minimum photon energy required to remove electron from metal surface, you will get 1. And if you have mentioned about 0 kinetic energy, you will get the second mark. This is a typical question. So you need to understand how to write down work function energy. You also need to understand how to state threshold frequency. For part B, it is given to us ultraviolet radiation of frequency 1.36 times 10 to 15 Hertz is incident in a vacuum on a metal surface. The power of radiation incident on the surface is this. Photoelectrons are emitted with a maximum kinetic energy of this one. Determine the number of photons incident on the surface per unit time. Very nice question. Number of photons incident on the surface per unit time. So in this case, we have the power. So the power is given to us, and power is equal to energy over time. So power is equal to energy over time. So in this case, we need to find energy per unit time. So simply you can say energy is representing the total energy. So this is the total energy. So I'll be using for this one total energy for better understanding. So this is the total energy falling on the surface of the metal per unit time. So we can say total energy per unit time. So this one is unit time, means 1 second. So we can also write down per unit time. Total energy per unit time. Per unit time means 1 second. Total energy means that this is equal to number of photons reaching the surface times energy of single photon. So we will be writing this multiplied with energy of single photon. So I'll be just writing HF because this is representing energy of single photon. Divided by unit time means 1 second. So I'll be writing here, this is 1 second. Now from here, N you need to find out, and value of HF. So this is HF. So simply P, now you can simply see NHF, because this is 1 second. So we need to find out value of N. So N simply will be equal to P divided by HF. So N is the number of photons per second. So power is given to us, power is 8.36 milliwatts. So this is 10 to minus 3 divided by H is the Planck's constant, and Planck's constant is equal to 6.63 times 10 to minus 34 joules second. And in this case we have frequency of incident light, that is 1.36 times 10 to 50. Now if we solve this one, we will get our final answer, that will be equal to 9.27 times 10 to 15. I mean, this number of photons are reaching the surface in 1 second. So you can simply write down, this is 9.27 times 10 to 15 up to 3SF. Why we are using 3SF? Because given data, this one has 3SF, this has 3SF, this also has 3SF. So you have to use at least 3SF in your final answer. For the second part, we need to calculate the work function energy of the metal. Work function energy of the metal, and we have frequency of electromagnetic radiation, and also we have the maximum kinetic energy of photoelectrons. So simply you have to use photoelectric effect equation. Photoelectric effect equation means HF, this one is equal to kinetic energy maximum plus work function, and this is energy of the photon, energy of incident photon. In this case we need to calculate work function. So this is the work function. So work function simply is equal to HF minus K max, kinetic energy maximum of photoelectron. So we have in this case H, that is equal to 6.63 times 10 to minus 34, and we have frequency of incident radiation, that is equal to 1.36 times 10 to 15 minus kinetic energy maximum. This kinetic energy is given in joule, so simply we can use this one. If this was given in electron volts, so you have to convert into joules. So simply in this case we can write down, this is 3.09 times 10 to negative 19. Now if we solve, our final answer in this case will be equal to 5.93 times 10 to minus 19 joules, and our answer has to be up to 3SF. Because the given data, we have 3SF here, we have also 3SF here. So you can see 3SF. So this is our final answer. So simply we can say this is 5.93 times 10 to minus 19 joules. And if you have done this one, you will get 2 marks. Typical question. So this equation is very important for photoelectric effect. If any question you are not clear, write down this equation and you will be able to figure out the answer. For part C, it is given to us the frequency of the radiation incident on the surface in B is increased while the power remains constant. State and explain the effect of this change on the maximum kinetic energy of the photoelectrons. Pretty straightforward question. In this case, power is kept constant, but energy of each photon has been increased. So simply we can understand from here, we have discussed this point already. Power is equal to the total energy of electromagnetic radiation divided by time. So this is time. So total energy is equal to number of photons times energy of each photon divided by time. So in this case, it is given to us that frequency has been increased. If we consider the same amount of time, in same amount of time, number of photons have to decrease because power is kept constant. So in this case, frequency of each photon has been increased. If frequency of the photon increase, it means energy of the photon has been increased. And we need to compare that one with maximum kinetic energy. Means what is the effect on maximum kinetic energy. But work function of the metal in this case is also is constant. We're using the same metal. So simply you have to write on photoelectric effect equation. So we can write on HF, this is equal to K max times work function. So K max, we can make the subject. So the K max is equal to HF minus work function. So simply you can see from here now, if the frequency increase, it means this energy increase. So the K max also increases because we are using same metal. So work function is the same. So that's all simply you need to understand. So you will say greater photon energy, same work function. Greater photon energy, same work function, so higher maximum kinetic energy. So let me show you the answer, how you can write. So these points you can mention in your answer and you will get 2 marks. So you will get 1 mark for writing greater photon energy and same work function. Second point, because this is asking you state. So this is a statement, maximum kinetic energy increases. You will get 1 mark for this one, 1 mark for the explanation, because this is your statement. So this is your statement. And this one is explanation. So this is how these 2 marks will be awarded. For the second part, we need to state and we need to explain the effect on rate of emission of photoelectrons. But in part 1, we have already discussed that power is equal to NHF divided by time. As the frequency of electromagnetic radiation increases, so the number of photons decreases, and number of photons is linked with number of photoelectrons. So simply we can say number of photons. This is linked with number of photoelectrons. So this is linked with number of photoelectrons, because interaction between photon and electron is one-to-one interaction. So in this case, if this go down, this will also go down, because you can also, in a better way, you can say they are proportional. So we can use the sign of proportionality. They are proportional to each other. If the number of photons go down, so number of photoelectrons also will go down. So the rate of emission, so then we can say rate of emission in this case will decrease. Rate of emission decreases. If you have this much understanding, now we can write down our answer. In the answer, you can mention these points. So first you can say greater photon energy, same power, so lower number of photons per unit time. Each electron absorbs only 1 photon, so lower rate of emission. So this one is the statement, and the above one is the explanation. So this is the statement and this is the explanation. So if you write down these points, you will get 2 marks. And that's all for today's video. And in this video, we have talked about AC, alternating current. We have talked about quantum physics. I hope these questions are clear to you, and also you have better understanding of these 2 topics. If you found this video helpful, means if this video was helpful and this video helped you to improve your conceptual understanding and also give you better explanation of these questions, then please like and subscribe, because your encouragement is very important. And remaining 2 questions I will be solving very soon, maybe by today or by tomorrow morning. See you in next video.